LoRA rank is not a magic number. Sweep rank and alpha with PEFT. Then keep the smallest adapter that hits your validation target without wasting VRAM. You'll see how to connect the pieces into a workflow that tests rank and scaling choices against a target and picks the smallest adapter. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Many teams want model improvements without transferring or retraining an entire large model. LoRA with PEFT gives you that option by adding tiny adapters that change only a few parameters. In practice, this saves training time and GPU memory. The typical goal is simple. Improve a validation metric enough to matter, but keep the adapter small, so inference stays cheap. Intuitively, rank controls how many basis vectors the adapter can use. Alpha scales those updates. Together, they set adapter capacity and effective step size. Sweep too conservatively, and you waste VRAM. Sweep too aggressively, and you overspend on parameters that give tiny gains. Success looks like a tiny adapter that reaches a validation target and leaves headroom for other features. We will build a small, repeatable sweep. It creates a grid of rank and alpha settings, attaches a LoRA adapter to a tiny model, trains briefly, measures accuracy, and then picks the smallest adapter that meets the target. The code is intentionally tiny, so you can follow the logic, not wrestle with data pipelines. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Next, I show how to build the search space so you do not arbitrarily copy one rank and alpha pair. This snippet constructs a grid of LoraConfig entries so you can compare several rank and LoRA alpha combinations instead of guessing a single pair. It builds each candidate with the same target layer proj, keeps target quality next to the grid for an explicit stopping rule, and prints how many candidates will be evaluated and which configuration comes first. A higher rank raises capacity. A lower rank keeps the adapter compact. This output makes that trade-off obvious up front. Now we need a minimal model that can actually run a fast experiment and show how adapters attach. This example builds a tiny, runnable PEFT model and attaches the LoRA adapter so the sweep stays fast and inspectable. It uses in-memory X and Y tensors on purpose, then has build model return a PyTorch NN.sequential with a named proj layer, while PEFT inject adapter in model wires in the LoraConfig adapter. The printed checks verify the validation size and that the classifier emits 2 logits per example, so the training loop works as expected. Before training many candidates, we want a compact metric that measures adapter size in plain numbers you can compare. This code converts adapter size into a numeric measure you can track alongside quality. Trainable count tallies parameters where requires grad is true, the parameters the optimizer will actually update after injection, and the total count gives context, while share normalizes the adapter footprint for easier comparisons. This gives a simple cost signal so you don't pick larger ranks just because they feel safer. The visible output reports the trainable parameter budget for the current candidate. Counting parameters alone is not enough. We also need to measure model quality after a short training run. This snippet measures model quality after a brief training run so size and performance can be compared. Train eval rebuilds the model for one LoraConfig, trains only the PEFT-enabled parameters with AdamW, and evaluates accuracy on the small validation tensor. A fixed seed keeps runs comparable across candidates. Steps is intentionally small for the demo. Raise it for stability, or lower it to speed up the sweep. And the printed result shows the candidate's trained accuracy, so size is no longer the only signal. With size and quality measured, we can compare candidates and pick the smallest acceptable adapter. This code finishes the sweep by putting quality and cost side by side for each LoraConfig. For every candidate, it calls train eval, rebuilds the adapter with build model, counts trainable parameters, and estimates float32 adapter memory as VRAM MB to give a compact VRAM budget signal. It then filters candidates with past that clear target quality and uses choice to select the smallest adapter by parameter count and estimated VRAM. The printed output explains which rank alpha pair was chosen and why it's the smallest acceptable baseline. To map this tiny example to a real project, run the same sweep on a frozen transformer head for a real classification dataset such as SST or MNLI. Increase steps to a few hundred and track peak CUDA memory during training. That will show how the chosen rank scales to production workloads. What you just learned in brief. LoRa rank and alpha set capacity and scale for small adapters. Sweep them with PEFT to trade off validation quality against adapter size. Watch for noisy comparisons and use fixed seeds and enough steps to get stable signals. A practical next step is to run the same sweep on the SST dataset. Raise steps to 100 and log peak GPU memory so the chosen adapter fits your deployment budget. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.